these are the kind of calculations that, that we're interested in. And so I'm going to have a lot of examples of these because I like to have movies and pictures. That's why I got into CFD, right? So I can, because it's visually attractive. What I really like about this calculation is we were kind of negotiating with some industrial partner, and they had something they wanted us to look at, and blah, blah, blah. People were saying 6 months. I said, this is ridiculous. We've been funded to do this for several years. So I got really upset, and I couldn't sleep. So I got up at 4 in the morning. I had the mesh ready by 10. I threw it on 16,000 processors, and I had this movie by 4 in the afternoon. So 12-hour turnaround. All right, and that's what we're after. We capitalize on compute availability to turn things around rapidly. All right. So this is the same vendors. This part somehow connects to that. I don't know exactly how. It took me about 3 days to build that one. That was a harder problem, but this one turned out to be easy. And it's kind of interesting. You don't know a priori which ones are easy and which ones are hard till you start diving in. Small geometric details can make a huge difference. It's a very nonlinear phenomena, geometry, right? So we'll see some examples of that. And so that's really one of the, not only can we answer the fluid dynamics questions, we can also answer, the hard or easy question. So the outline, since I said the title was CFD, PDEs, and HPC, we're going to talk about turbulence to start with, and I'm going to talk about PD discretizations and solution strategies, or solver strategies, and HPC. And then kind of the second half of the talk will be what I would call the HPC part. It's really kind of devoid of the PDE, and it's more about how we are mapping our fluid mechanics problem onto high-performance computers. All right. So something that's, these are the equations we're solving. So let's start off with a PDE. This happens to be the incompressible Navier-Stokes equations that govern the fluid velocity and the pressure. Here's the pressure. They are nonlinear. So we have this U dot grad U here, which is a really highly nonlinear process, it turns out. And so the key algorithmic architectural issues are, first of all, we have an unsteady solution, so it's evolving with time. We have many time steps, which means we can amortize preconditioners, partitioning, data partitioning, and so on and so forth. We have this divergence of U equals 0. This is the incompressibility constraint. This has very deep implications all the way down to the HPC end of things for the following reasons. So divergence of U means you can't stuff more stuff into a box than's already there. So for instance, if you have a pipe and somebody pushes on one end, the flow comes out the other end instantaneously, right? Now in physics, it doesn't really happen instantaneously. There's an acoustic wave and then boop, 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 and at speed of sound, then it starts coming out. But this model has gotten rid of that fast acoustic wave and replaced it with something that's infinitely fast. And the net result is we get a much easier system to solve. It's linear and so on and so forth. But it does have deep implications, which is that we have global communication everywhere. Every processor knows if we've suddenly applied a boundary condition at one end, boop. So that implies global communication. No matter what happens, one person says, oh, I'm opening up, everybody has to get out of the way. Always global communication, every point to every other point. So that's a rather deep phenomena that's intrinsic to this model, not exactly to the physics. Okay. And then another issue is that we have this singular perturbation. So the highest derivative here is multiplied by a small number. Reynolds number is typically large. So even for a pigeon, Reynolds number is 10 to the 6th. Okay, so which if we didn't have this term, we'd have one boundary condition in space. But now we have one on every boundary. So the singular perturbation coupled with this nonlinearity is what gives rise to this large range of scales. Okay, and the large range of scales means we're going to be solving very large problems. All right, so how do we do that? We treat the nonlinear term explicitly in time. There are very good reasons for doing that. First of all, it's nonlinear, non-symmetric, and the time step constraint imposed by doing that is not too severe. So it's okay to do that. We move everything else over to the left-hand side, and we have a linear system to solve at every time step, not a nonlinear system. So that's good, all right? And we can do some further decoupling into 3 components, 3 so-called easy problems for the velocity, and then a Poisson equation for the pressure. This is the one that has the global coupling that, that is quite computationally and communication dominant. And we'll talk about that as we go on. Okay, so fluid dynamics governs a broad range of physical phenomena. I mean, it's everywhere: atmosphere, ocean, automobiles, airplanes. And the majority of the fluid flow is turbulent. Almost everything is turbulent. If you kind of just run the numbers for flow in the exhaust pipe of your car, you say, no. You work it out, speed of, say, a meter per second, 1/10 of a diameter, 1/10 of a meter, 0.1, and then you divide by the viscosity, which is 10 to the minus 6, boom. Suddenly you're there, 100,000. Anything above 1,000, you're starting to transition into turbulence. So it's very easy to get it turbulent flows. Okay, so these things are non-repeatable. They're chaotic. That's an unfortunate thing. But we observe that they are somehow repeatable in the mean. So very often we're interested in the mean, all right? And so one thing that can be done is to use Reynolds average Navier-Stokes equations. Right? They're an excellent model for computing the predictable cases. And they can be 100,000 times cheaper than what we call large eddy simulation, which is a little bit cheaper than direct numerical simulation, where we resolve all things, all scales. So the reason I talk about this at this juncture is because factor of 100,000 is something nobody can ignore, right? If you're using Mira, which has 800,000 cores, let's suppose you're using 100,000, and somebody else comes along, they run the same problem on 1 core of Mira, it's like, oh, that doesn't look so good. So you really want to know when you should be using Mira and when you should be using your laptop, okay? So we'll see some examples of that. So this model decision is quite important, and it's something that requires domain expertise, right? Even I'm not an expert, by the way. I defer to the mechanical engineers that I work with. They know when RANs will work, and they know when it won't work. And sometimes it hits them right in the face also, by the way. We'll see some examples. Okay, so so that factor of 100,000 is why I bring that up. Okay, so here's an example of sensitivity. This is a geometric sensitivity. So Argonne has what we call the fish tank. It's 1 meter by 1 meter. This picture doesn't look like it. That's actually square. It's 1 meter by 1 meter, and then 1.6 meters in the lengthwise direction. There are 2 jets coming in the bottom. They can be at different temperatures. And the question is, how do these things mix? That's important for certain industrial applications. It turns out that the RANS codes can run somewhere between 10,000 and 100,000 times faster for this particular problem. And the main reason is when we simulate it, one of the main reasons is when we simulate it, we're simulating it in an unsteady way. The first thing you have to do is fill up the box with turbulence. So if you have a tiny straw in a really big room, okay, you're going to be waiting for quite a while. And experimentalists can always defeat CFDers just by making their box bigger. You can do a back-of-the-envelope calculation. Our cost goes like the length squared, the length scale to the 6th power. So a small increment in the size of this makes our problem much more expensive. If instead of having 2 jets, if we had had a whole floor of jets, our work would have been much cheaper because we would have filled the box up faster. Okay. The RANs doesn't matter. They solve a steady state, so they go straight to steady state. So let's look at the results when we look at the velocity profiles for 2. Now this is a code-to-code comparison. We've also got experimental data, finally. It took them a very long time to get this experimental data. We were up and running with CFD results years before the experiment was ready. So if we look at the RANs versus the LES, they actually look pretty good. At the lower one especially, it looks quite good. The upper one, a little bit of difference near the exhaust, which arguably is not really a region of interest. So, for a factor of 10,000 less, you could do the RANs, which is I believe, the red curve, or you could do the unsteady one. All right, so guess what? When they built the experiment, they didn't build it this way. This was the as designed, this was the as built. And here's the solution for as designed, and here's the solution for as built. And this thing is very unsteady. These things waver around. Guess what? RANs didn't even converge for this. So the time for RANs in this case was infinite, right? Because it didn't converge. We knew that our code would converge because for us it's no difference. We build the mesh, and sure enough, we get this answer with no particular problem. So this tiny geometric perturbation resulted in a huge change, right? this solution is a factor of 10,000 times cheaper than this one. Okay. But it's a good argument for actually being able to solve these unsteady problems, and we of course do that in parallel. All right, so here's another example that definitely won't, RANDs would never pick up. And it's flow in a curved pipe, flow that's almost turbulent. Well, actually it is turbulent, but so what they found was that, and this one was found experimentally, by the way, that there is a certain Reynolds number where the drag actually goes down once it transitions to turbulence instead of, usually drag goes up when you have turbulence. But there is a certain Reynolds number where the drag goes down. The guys that I work with at KTH in Stockholm, they're very good people at analyzing instabilities. And usually if things go down, it's because there's some kind of organized structure. It's unsteady but organized. And so that's what they're pointing to here, is that there's organized structure in the turbulence in this curved pipe in this case. So this definitely cannot be done with RANDs. All right. So the good news is that large eddy simulation and direct numerical simulation rely on very little modeling, so none in the case of DNS. We just have these equations. They've been around for 150 years. They're highly nonlinear. They're hard to solve, but we have parallel computers. We can do that. We have a broad range of scales, and their success is largely tied to that of parallel computing. So prior to the mid-1980s, the majority of fluid flow simulations were 2D. Definitely not turbulence. You don't get turbulence in 2D. You have to be 3D. Okay? So, all right, let me go to, well, okay, so we've already looked at this part. Let's go on to a few, just a few more turbulent examples. So this is a heat transfer example. A lot of our problems are in heat transfer. This one came from Argonne's advanced photon source. They have very big blocks of copper, joule heating. The blocks of copper get very hot and they pump water through them. They found that they could insert wire coil inserts, and for the same volume of water, increase their heat transfer by a factor of 4. So they came to us and said, can we explain this? And I would like to say the answer is yes, we can explain it. So far, all I can say is we've been able to reproduce it. We've been able to reproduce almost every dot on this. I mean, we've sampled it, and we always nail it, no problem. And now we're digging in deeply because we have a microscope. We can look at everything. We can do time average. We can do a lot of statistics. And we have some hypotheses about what are the principal things that influence this. And so that's one of the things we're digging into. This is another example. This, again, from the Swedish group. This is a very hard thing to compute, is the pressure recovery in a diffuser. There's experimental data from Stanford and our results. OK, we can get that, no problem. This is a big calculation, several million node hours on the BGP. Same group now is doing high Reynolds number flow past a airplane wing section. So this is Reynolds number 400,000. You can see the range of scales. So if you think about it, I counted these up. I'll just ballpark estimate here. Let's say there are about 100 vortices across here. And let's say you need 5 elements per vortex. You're talking about 500 elements in this direction, or 500 points in this direction, a few thousand in this direction, and a couple thousand in this direction. So that's how you come up to 3 billion, trying to resolve all these scales. We are doing a fair amount of work with the ETH group in Zurich on engine simulations. So they've started off initially with, they do a lot of combustion, by the way, but these simulations are without the combustion. They started off by comparing against some experimental data that's available. And one of the more exciting things for me was this calculation here. So now, after getting a proper charge of the right chemistry into the cylinder, they compress it. They close the valve and compress it. So this is actually, it's not an incompressible flow. It's what we call, well, it's what we call the low Mach number formulation, but it's compressed flow. And I remember as a master's student back in the early 80s when my advisor said, we still don't know what compressed turbulence looks like. And finally, we were able to answer that question. One of the more interesting things is that as you get up to top dead center, the flow gets more and more turbulent. Why is that? Well, the density goes up. That's the short answer. The density goes up, and the result is in a higher Reynolds number. It has rather deep influence on the heat transfer around the walls and the top and the bottom of the cylinder. And the guy who has done this calculation has already filed some patents based on his insight from these calculations. Okay, so the same group, we're now looking at, these are our latest results, and they're extremely pretty, and then we'll go on to some algorithmic things. But so this is the mesh. The hardest part of meshing this geometry, this is a General Motors configuration, and the experiment now is at University of Michigan. So they have a lot of data for this particular configuration. The hardest part was to mesh this with the valve stem coming through these intake and exhaust ports. Once we got that taken care of, you can see here these horseshoe vortices around the valve stem. They break up into hairpin vortices. What's really fascinating here is this has implications when an air-fuel mixture is coming in here. Things are pretty well stirred by the time they enter because of the amount of turbulence that's in the intake port. So we're going to be investigating that more and more as we go on. So he's now looked at various Reynolds numbers. You can see more turbulence as you get to higher RPM. And then now we're drawing the stuff into the combustion chamber. And again, generation of a huge range of scales, which you can see here. Okay, so this is about 4 million elements. It's about 1 billion grid points, 800 million, I think. All right, so let's look at the cost of doing this. What are the costs? That's kind of what we're interested in here today. So we have 3.9 million elements. These are polynomial order 6, so they have 216 grid points per element. And it's about 840 million points. It's about 100 hours on 131,000 cores of Mira, so 1/6 of Mira, roughly. Just to go for 180 crank angle degrees. So if you did the full, since it's a 2-stroke engine, full 720, about 400 hours. All right. So the question is, can we run faster? And that's what the purpose of this talk is. All right. So what about better algorithms? Well, one thing we could do is try to lower n. We can do that via high-order discretizations. Faster solvers, we want to lower iteration counts. And what about more parallelism? All right. And so that's really the thrust of the talk today. Now, in fact, this one, it doesn't have the best possible solver. I mean, it's got a good solver, but not the best possible, I think. The n is actually pretty good. So I'm going to argue each of these points as we go forward. OK. So these are relatively deep considerations. So higher order for PDEs, right? And it's deep in the sense that, well, in a sense that we'll see. So the whole point of higher order is to reduce the problem size, i.e. n, the number of grid points. And hopefully that corresponds to a reduced cost also. Okay? And then fast multi-level solvers. That's very important. You need scalable solvers, right? If you're trying to do a direct factorization, let's just take an n by n matrix. The cost scales as n cubed. As the problem gets bigger, that's definitely not going to scale well, right? So we want order n solvers. So if I double this problem size, my cost goes up by a factor of 2, but presumably I can use twice as many processors, keep my runtime fixed. And then more parallelism. The question here really is how much more. In the second half of the talk, we'll talk about that.
So what type of a method are you using for discretization?
I'll get to that in about 4 slides. OK. And I'm not going to dwell upon it, but I give it as an example. OK, so the influence of scaling on discretization. So this is one of the goes back in time slides. Kreis and Oliger observed this back in '72, long before. Now, it's not true there were no parallel computers because the ILIAC 4 was around by that time, which was a 64-processor parallel computer that I don't know if it was actually being well used by '72. I don't think it was till the mid-'70s when people actually got codes to run on it. But there were some very important calculations done on that machine. But anyway, so Kreis and Oliger wrote a paper, and one of the statements in the paper was high-order methods can efficiently deliver small dispersion. Well, no, sorry. This whole argument is Kreis and Oliger, so let's go through the argument. Large problem sizes are going to be more efficiently solved by high-order methods. That was their argument. Okay? So let's look at it. Large problem sizes enabled by these very large parallel computers allow us to propagate small-scale features over long distances. So if we have some size lambda, we want to go over distances L, which are much, much greater than this should be lambda here. All right? If the speed is 1, we can always non-dimensionalize, then the final time is going to be L divided by lambda. I have a little thing. It's moving at speed 1. It's going at distance L. Okay? So the dispersion times accumulate linearly with time. So imagine time is 1,000, right? So I want my final error to be, say, 10 to the minus 2. I have this big multiplier, 1,000 here, which says my numerical dispersion error has to be 10 to the minus 5th, right? So most people rightly argue, do you really need 10 to the minus 5th? I'm happy with 10 to the minus 2, right? I definitely don't need 10 to the minus 12th. My data is not that good, okay? The bottom line is you need 10 to the minus 2 in your final answer, right? And by this argument, that says that your numerical dispersion error has to be 10 to the minus 5th. And when you have 10 to the minus 5th, you're definitely on the asymptotic part of the convergence of these numerical methods, right? You're well into where the Taylor series terms are rapidly diminishing, and that's where high order and low order part ways. So our particular one, our particular method, just to give some context, is the spectral element method. The easiest way to think of it is a high order finite element method implemented in a certain way. And particularly, we've implemented it in terms of tensor product bricks because we can evaluate operations very fast with tensor product bricks. Okay, we can keep our operator evaluation costs. To do a matrix vector product for the Poisson operator with spectral elements requires 6 memory references per grid point. Same as a 7-point finite difference stencil. Okay. Typically, we're running in the order of 4 to 15. Some of our users run as high as 20 or 30. And little n will be used throughout this talk as the number of points in the problem. In this case, it's the total number of elements times n cubed. Okay, and we have this, the storage is O of n with small constants, and the work is O of n, but the only work that is scaling as the polynomial order is cast as matrix-matrix products. So think about it. I multiply 2 matrices together. They're both n by n. I have n cubed work, and I have n squared memory references. So I have a computational intensity of n, right? And it looks more, the cost looks more like n squared than it does like n cubed, okay? So it has a favorable work constant. Okay, so here's the argument. These things converge exponentially fast. Here's an exact Navier-Stokes solution. This is a semi-log plot, so if you double the number of points in each direction here, we come down by 4 orders of magnitude, a factor of 10,000. If you had a second order method, you'd come down by a factor of 4. All right, so hugely qualitatively different. But again, I'm very sympathetic to the argument, well, I only need this. I don't actually need 10 to the minus 12th. But we've already kind of justified it through the Kreis-Oliger argument that you probably want to be down around here. Okay, and then the other kind of interesting thing is that when I was a student, we were all told, well, the problem is that these things converge exponentially fast, but they do not converge exponentially fast for pointy functions, right? Because the Fourier coefficients don't die exponentially, they only die algebraically. But it turns out, and this was in the Gottlieb and Orzeg's, the first book on spectral methods, this is an example at the end. They said, yeah, that's the theory, but guess what? They actually work pretty well, even for pointy functions. Okay, and the reason for that is that a lot of the energy that's being transported here are very smooth functions. Once you do the Fourier decomposition, it means you're making almost no error with these spectral methods in the low wave number modes. So you're getting the low ones dead bang on, and yeah, okay, we give up. Everybody sacrifices on the high frequency content. So that's why these things are actually viable when they might not have a right to do so. Okay, so what about nonlinearity? Does this linear example extend to the nonlinear case? So a group at NREL did a study. They took the classic turbulent channel flow between flat plates, for which we have gold standard answers. So direct numerical simulation done by Mosier, Kim, and Mansour in '99 at several different Reynolds numbers. So this is Reynolds number 180 based on the boundary layer thickness, or the shear velocity, I guess it is. So this is the gold standard answer here. Here's the spectral element method. And you can see, that here's the finite volume method, second order. That's a popular code. And this is the number of points in the wall direction. So every time you double the number of points in the wall direction, you double the number of points in all directions. So the cost goes up by a factor of 8. So here we see we need 1/8 as many points to get this answer. We need 1/8 as many points to get this quality answer, and then presumably the same is true for the next one. So we've reduced the number of points by an order of magnitude by going from second order to this 7th order method. Okay. I could not have done this study because I wouldn't have been able to give a fair shake to the second code, but that group actually uses that second code in production. Well, what about, how does that translate into time, okay? So they also did a timing study. Both codes are essentially the same cost. So the number of grid points is fixed here and then strong scaling. So here the red curve is the finite volume code, the black curve is the spectral element code. So essentially the same cost over a broad range of processor counts. Now, by virtue of the fact that we can use 1/8 as many points, we'll run 8 times faster. So high order is one way to run faster, okay? You have to be careful, right? It's a very carefully constructed argument. It's not always going to be true for every problem. So let me give you an example where it would not necessarily be true. Suppose you wanted to do flow past the cylinder. Guess what? The flow past the cylinder always separates at the exact same angle. It doesn't matter how good or, you know, the physics is such that that thing just, it's like falling off a log, okay? You don't have to go in with a fine instrument. So it does matter what the problem is, but it is realizable. Okay, so that's the high order, and that's why it's relatively deep. It's not an easy slam dunk argument. Okay, and then fast multi-level solvers, I'll just talk a little bit about that. I'm not going to go into details, but I'll just give you some idea of the roadmap. We're using multigrid with additive Schwartz-based smoothing. So we had an additive Schwartz code, and then we decided, oh, we really want to make it multigrid. So it's really just multi-level Schwartz is another way of thinking about it. But our smoother means we solve the PDE on this boundary for the residual. Okay, so the right-hand side is the residual, which means that when I invert the operator, I get the error. Okay, so I don't know the error on the boundary, but I'd like to guess it's 0. So what you do is you set you solve in this little domain the equation for the error with 0 on the boundary because it's the only thing you know, right? Which means that you're taking out all of the wiggly component, and what you're left with is the error induced by the boundary, by the residual error on the boundary, which corresponds to the Green's function, the decay of the function to the interior. That tells you two things. One is, for this problem, for Poisson, which is for the pressure, it's smooth. So it's a good smoother for multigrid. Secondly, it tells you that more overlap is better because you're interested in the error here. Okay, so more overlap is better from that perspective. It turns out with these methods, universally, everybody uses one grid point of overlap. In other words, they have one extra degree of freedom in the neighboring domain, and then they set their boundary condition on the other thing. And that's what people have found that just by trial and error. Every code, everybody I know who uses it in practice, that's what they use because the cost goes up too fast if you have a very wide overlap. So then the theorists came back and said, why the heck does this thing work so well? And so there are papers on, you know, why this works for small overlap, even though the theory says it should be wide. Okay, so the next part, which is really interesting, is the coarse grid solved. So to get this thing to work, at the bottom we have linear finite elements for every spectral element. And so if you think about it, I have 1 million spectral elements. It means I have a global coarse grid problem, which is 1,000,000 by 1,000,000, sparse. And if I'm running it on 1 million processors, then I have a problem, AX equals B, on 1 million processors that is of size 1 million. So normally if you walk into the room and you say, I want to run in parallel, how many processors can I use? My problem is 1 million by 1 million. Nobody would ever say, use 1 million, right? Nobody would ever say, one row of the matrix is the right thing to do. So one idea would be, I've got this 1 million by 1 million problem. It's very sparse, and it's already spread out over 1 million processors. Why don't I gather it together to some respectable number of processors, like let's say 100, and then then I can parallelize that. So you could do that. However, there's a cost associated with doing that, which is migration of the problem onto the subset. Turns out, in our experience, the best thing to do is to just go ahead and solve it while it sits there, and design the algorithm to be communication minimal. This problem is intrinsically a communication problem. First of all, it's an all-to-all, right? Because the inverse of this guy is completely full. All right, so it's an all-to-all. The data is 1 degree of freedom per processor, roughly, if I'm at that level of granularity. And the output is 1 degree of freedom per processor. And it's all-to-all. So it's an all-to-all communication. The question is, how can you do it? We have two methods. One is a direct method, which is pretty good up to about 100,000 processors. Involves a sparse factorization of the inverse of A0. That's kind of interesting that such a thing exists, even though that A is not. And I lie when I say sparse, by the way. Sparse normally means a fixed number of elements per row, right? And so our sparse factorization is what we call quasi-sparse. It's just something that's less than n squared. So it's end of the 3/2 in 2D, end of the 5/3 in 3D, okay? That works up to about 100,000. And then after that, if we have a larger problem, we switch to algebraic multigrid. That works quite well. Okay, so that's the coarse grid solve here. Okay, so we put it all together. Here's our first simulation with 1 billion grid points. This is 3 million spectral elements. We ran it on anywhere from 16,384 up to 131,000 processors on Blue Gene P. Took 15 iterations per time step. So we have a nice, robust linear solver. It's a complex domain. So it's these 217 rods with helical wires wrapped around them, spacer wires, okay? And then the flow goes through it. Coarse grid solved with AMG, algebraic multigrid, takes less than 10% of the runtime on 131,000 processors. So we have that one under control. Okay. And the strong scaling looks like this. So we're at about 80% parallel efficiency at 131,000 processors. For me, if you're showing a plot like this, you always got to tell the reader how many points per processor or how many points for the total problem, right? I can make this problem look bigger in a couple different ways. Well, the easiest way would be to run a bigger problem, right? If I run a big enough problem, I'm going to have perfect linear scaling. Okay, so, and that's kind of uninteresting in some sense, because the first question that comes to your mind is what happens if you keep going? And of course, it looks bad. It looks bad for everybody. It's a given that it looks bad. So the interesting question is how bad and when, and this is where all the interesting stuff is happening. So we don't want to hide it. We want to show it and then discuss, is there a way we could make it better? Okay, could we do more parallelism? So let me give the answer before I go into how I got the answer. So this simulation has 3.9 million elements. So the granularity of our spectral element method, we have to have at least one spectral element per processor. So in principle, I could run it on 3.9 million processors. I'd have one element per processor. But this is polynomial degree 6, so I have 216 points per processor. I know a priori that's too low. How do I know that? I know that because you'll see how we're going to figure out how I know that. But you wouldn't know that ahead of time. So for instance, if it were electromagnetics, I can tell you that would be okay. Okay, why electromagnetics and not for us? So for us, our cost is dominated by the Poisson solve, by the pressure. It's a scalar equation, one unknown. Electromagnetics, you have 6 unknowns, right? The three components of E and the 3 components of H. So although I have 216 points, with electromagnetics, I would have 1,200 degrees of freedom. I have a lot of work, but I only have 6 messages on each brick to exchange. So my work per unit volume has gone up, and I can amortize the communication costs. So you have to know a little bit about the equation to know whether a priori, to project out if you can go to this level of parallelism. So for a problem that's dominated by Poisson, I can tell you that this is too low, at least for this machine. All right. So we need typically around 2,000. Okay. And we're going to, you'll see. We're going to figure that out by looking at a model problem. So before I said one way you could make the code look better is to run a bigger problem. So we actually did that here. We ran a bigger problem because we wanted to go out to 1 million MPI ranks. And one of my ace, I don't know what you want to call him. He races cars, but he also likes to run fast codes. So my ace driver, let's call him that. He said, it just doesn't look good if we have 40% parallel efficiency at 1 million processors. I go, yeah, but the point per process is so low. He goes, doesn't matter. People won't remember that. All they'll remember is 40%. I said, okay, so we bumped the polynomial up, and now we're at 2 billion grid points, all right? And now we're at 60% parallel efficiency here, okay? So we have 2 curves, the green curve and the red curve. So the red curve is running 1 MPI rank per core. The green curve is running 2 MPI ranks per core. We've also run 4 MPI ranks per core, and it kind of rolls over here. I didn't show it here. I should have done so. And which of these is the interesting curve? Well, the red curve has better strong scaling, but it's not interesting because it's universally slower than the green curve. So I put it here as a point of reference, but the right one to pick is always whatever is running the fastest, right? There's no point in messing around. The code is a mixture of CG and multigrid. That's important. And we're at about 2,000 points per rank, and we're getting 60% parallel efficiency at this point right here. Okay? And we'll see that that's more or less what we expect we should get for this code on this architecture. Okay, so I always ask, you know, will this scaling continue, like the weak scaling or strong doesn't really matter? Is it the best we can do? You know, what exactly is better or even good? And so one thing is good node performance. So I'm not talking about node performance at all here, but that's a really big issue, especially on modern machines where we're starting to have very, very complex nodes. And then strong scaling to large processor counts. So we want to use as many processors as possible. We had that other problem with 800 million points. We can't run, we probably can't run that one on 800,000 processors of Mira. So strong scaling is ultimately limited by costs that don't go to zero as n over p. So if n is the total number of points, p is the total number of processors. If I fix n and increase p, then this term is going to zero. My time should scale if it weren't for these two. In other words, if I double p, then my time should go down by a factor of 2. That's strong scaling. That's what we want. Why isn't that happening? Well, there's a constant that's floating around, which is communication overhead, other overhead like memory latency on the GPU, some other Amdahl law features. And then there's also the inner products and some of the multigrid stuff that scales like log p, so that's actually going in the wrong direction. Okay, this one can be mitigated by communication hardware. And so we want to understand why we can't get there, or you know, what's keeping us from doing more. So the last part of the talk then is the performance analysis. How can we judge if we're getting any speed up? So this is instructions for everybody here. And it's for all my students, I do the same thing. The obvious answer is the following. Fix the problem size. In other words, you have a problem you want to solve. Run it on a certain number of processors. Double the number of processors. Run it again, run it again, right? And you'll see where you reach the point of diminishing returns, right? Okay, and hopefully you aren't already at that point, because that means you should go backwards, right? Run it with fewer processors. If you don't try, you don't know. So that's the point. So then the second part is to ask yourself, why am I not seeing more speed up for a given problem size and number of processors P? And we have built into our code a suite of tests which give us all the communication parameters, give us the flop rate and everything. So I can tell a user in the field, oh, okay, you know, he says, it's a common question. My code's not speeding up. You know, I've doubled the number of processors. And then he describes the problem size, and I say, seems like that doesn't sound right. So I ask them to run the tests, and then I get the data back, and I can figure out what the hardware looks like. But the funniest one was this one. I had a guy, he was a good user. He'd been using our code forever. He knew all about it. He said, you know, I bought this machine. It's a 16 processor machine, and I get good speed up to 8, and then I don't get any speed up at 16. And his problem wasn't small. Okay, so guess what happened? It was I guess it was 2 cores per, what would it be? It was dual cores, right? So the way the code ran, it used 1, 2, 3, 4, 5, 6, 7, 8. And then when we went to 16, it used the second core on that chip. There was no resource. There was no bandwidth. So he did not have enough memory bandwidth to use the second core. So it was perfectly flat. He couldn't use that. So I'm not talking about that second scenario, by the way. I mean, it's really important. But the reason I'm not talking about it is because it's messy. We definitely worry about it. All right, so 2 runtime scenarios. We have a fully populated cluster. This will be important for my last couple of slides in my talk. With this fully populated cluster, you have a job on every node. All right, well, there's not much you can do here. You can't increase the number of processors, right? So you just make the nodes run as fast as possible and squeeze it all in and hope that you can do that. And then the other runtime scenario, these are both, I would consider these both to be HPC, viable HPC scenarios. There's the large supercomputing center. The job's not using all nodes. Okay, so why did you stop at P and not go to 2P? That's exactly the question we're trying to answer. Incidentally, in this scenario, you can't tell the difference between this many processors and an infinite number of them, right? You're not using them all, you can't tell. Okay, so we're going to look at a very simple Poisson model problem to get insight. So this is kind of the PDE plus HPC. So we're picking a PDE. I like this PDE because everybody knows it. Everybody knows the discretization. And then they can extrapolate to their own problem from this discretization. So here it is. It's 5-point finite difference. However, all the analysis is for 3D. It's only 3D that matters. The cartoon here is 2D. So we're going to have n over p points on each processor. We're going to assume everything's perfectly load balanced. And then we have to exchange data with each of our neighbors. So there'll be 6 neighbors. In this picture, it's, oh, that's a bad picture. It should say n over p to the, it should be n over p to the 1/3 because I have n over p values on this processor. Okay, so in other words, so think of it this way. I have 1,000 points on each processor, 100 points on each face that need to be exchanged. That's an interesting number because 1,000 points, keep that in mind. 1,000 points, what's my message size? 100 words. Right? So we'll hang on to that little example because it's relevant. It's right in the ballpark of where we want to be. We want to be down at 1,000. We prefer to be down at 100 if we could. Okay, so I'm using what I learned last week from Bill. It's called the postal model. For communication, we'll talk about that in the next slide. But there are 2 p-processor solution times for endpoints, 2 models. One is where the time for p-processors endpoints is the sum of these 2. So my arithmetic time plus my communication time, meaning I have no overlap of communication and computation. And the other is I take the max, all right? So I overlap computation and communication. In either case, an interesting breakpoint is where TC equals TA. Preferably, I'd like TA to be bigger than TC. So TC should be subdominant, all right? And TA, we're going to assume perfect parallelism is, in this model, is just the time on one processor divided by P. And then TC is the total communication cost. So it's the sum of the time it takes to communicate the words or the messages of length M. Okay, so these are blue water ping pong tests. And we're going to look at these curves quite a bit because they're really quite interesting. There are a lot of details that are interesting here. But the first thing we're going to do is take 2 asymptotes out of this, and we're going to build a model. So the model captures the asymptotic behavior. All right, and this model, this is what's called the postal model. It's a linear communication model. If I send a message length M, the cost is alpha star in seconds plus beta star M, where M is number of 64-bit words. So this is in seconds per word. Alpha, clearly as M goes to 0, I end up with alpha star. I would hope that my time goes to 0, but it doesn't because of latency. And latency is, there are many sources of latency. The alpha value is over here. In fact, this red curve, I shouldn't have put it here. This is, so what is, this ping pong test does the following. Node 0 sends to node 1, and that produces the purple curve. Does it for varying message lengths, and it loops over time to make sure it's accurate and so on and so forth. And then it sends to node 2 and so on up to node 511. Okay. So once I get off node, it sends to, well, MPI rank 511. I jump up to this curve. So this is my interprocessor latency here, internode latency. All right. One thing to note here is that it doesn't cost as much to send something to a process that's on my node, right? Even with MPI, I mean, it's faster, okay? And then I suddenly pay when I go off node, all right? Okay, the other thing to note here is we jump up here at a certain, what I call a switch point. This is about 250 words in this particular case. And we'll talk more about this jump in a second, okay? But our very simple model just captures this asymptotic part. The asymptotic says, the beta part says if M is very large, so I'm going to send 1 million words, I send 2 million words, it costs twice as much. Down here, I send 1 word, I send 2 words, there's no difference in cost, right? The breakpoint between where there's no difference in cost and there is a difference in cost, I define as M sub 2, which is simply alpha over, typically alpha over beta in this model. It's a little bit different. Here, the breakpoint actually is around this. You could justify that this is the breakpoint. Everything less than here is a short message. Everything here is a long message. So 250 words with our 1,000 grid points per processor, every message is short, right? That's good. This is about 3 times more expensive than this one. So that breakpoint is kind of is important. So the model is simple and maybe perhaps simplistic. It's general because it definitely captures these 2 asymptotes. Nobody can argue that those 2 asymptotes won't exist. It doesn't capture contention effects. Particularly, it doesn't capture contention effects within one node. Lots of messages leaving a node. Okay? Are these important? Probably on rich nodes. Right now, what we do is we model ideal performance, and then we investigate departures from the ideal. So more complex models depend on the number of processors, the runtime topology, which is rarely known. your processes are usually scattered around the network, except on BlueJean. It depends on other jobs in the system, except on BlueJean, because on BlueJean you have convex partitions. Nobody else's data traffic is going through your network. Okay? And it depends on the node architecture. Just to let you know, there are papers out that discuss these things. So Bill and Luke and Philip have a forthcoming paper, but I mean, I know the meeting is still in the future, right? You know, where they, and when I first read this, I took offense because I read it as, it is time to retire the ping pong test. And I say, I do the ping pong test. And then I realized, oh, it was a question. Is it time to retire the ping pong test? So you can just Google that, and well, at some point you'll be able to Google that and find it. And then this one, same thing. So what I'm going to talk about in all of this is in this paper. Again, you can Google it or get it from me. Okay. So let's talk a little bit about this breakpoint. I think this is really fascinating. Okay, this is on 1,024 processors, 1,024 MPI ranks, even though the test is going only from 0 to 512. And what's happening here? We're switching from what we call the one-way message to the three-trip message. So the three-trip message, let's talk about the one-way message. It says, I'm sending you one word. Got it, no problem. I'm sending you 1,000,000 words. Oh, I can't deal with that. You better tell me before you say, okay, I will be sending you 1,000,000 words. Are you ready? And you write back, yes, I'm ready. Okay, here they come. That's the three-trip one. It's going to take 3 times as long for that exchange to go on. All right. So how many words could I send you if it's not just one? I love, one thing I discovered with IBM, they really forced our hand in the mid-90s, I think it was. They could handle almost no words. You know, you flooded their buffers. It was terrible. So we had to change our coding style a little bit to make sure we didn't flood their buffers. But it depends. You know, somebody's going to make some choice. The thing is, if I have 1,000 processors, I have to be ready to receive messages from 1,000 other processors. Cool. Okay. Make up a number, 256 words, 1,000 processors. That's how much memory. Now suddenly it's 1,000,000. Uh-oh. I have to declare that, I have to multiply that memory footprint by 1,000, right, to go from 1,000 to 1,000,000. So the little piece of code doesn't change at all. It's still going from node 0 to 511 or 512. But now if I change the number of processors, this buffer is going to get smaller, and this curve should look different. Yeah, so here's blue waters. Now the switch point's at 25. Uh-oh, suddenly, if we're going to run on 32,000 processors with our 1,000 points per processor, and we're sending a face which has 100 words, every message now costs 3 times as much. All right? I've just lost a factor of 3 in scalability. Huh. Now here's what I find fascinating. None of the processors are ever going to talk to all 32,000 processors. So we really don't need to allocate all of those buffers. If we do it in a smart way, where we kind of accumulate a tally of our favorite, your favorite travelers, we could allocate the buffers for them and stay at the one-trip message. So then you could strong scale. Super critical here for strong scaling. I need to lower the alpha because my messages are all short. I hardly have to worry about beta at all. My messages are all short. So if we really want a strong scale, more emphasis on what's happening here than what's happening out here. That's what we need. All right. Now, let me go back a slide because you'll see why why this slide made some sense back then. Yeah. Okay. But now you're a vendor. It depends. Are you marketing to these guys or are you marketing here? Right. If you're marketing here, you might care more about bandwidth because you have a lot of work per processor. But here, if you want a strong scale, which is what we'd all like to do, run faster. Paying attention to this switch point. If you have 1,000,000 processors, the PDE doesn't know the difference. All right. And so just here are the raw numbers. So the time jumps up by a factor of 3, roughly, in both cases. And the switch point is roughly 250 words here and 25 words here. I don't know the exact algorithm for allocation of the buffer space. But it clearly makes an impact what value of P you are using with this model. OK. One more thing. Another argument for, or maybe against, I don't know which it is, for a simple linear communication model is sometimes some machines have a lot of system noise on their ping pong tests. So these are ping pong tests for several decades, and they have all been non-dimensionalized by the rate at which I can do work, by the time it takes me to do multiply. So this is basically the inverse of the flop rate on my code. All right, so you run your code with just one processor, you find out saturated flop rate, take the inverse of that, that's your arithmetic time, and then you divide your alpha and your beta star, the physical ones, by the time, and then you have non-dimensional numbers there. Okay, and these are the non-dimensional parameters for the last 30 years. So, you know, we've gone from latencies of 5,000 microseconds, 6,000 microseconds, down to about 2 microseconds. Pretty good. You can compare that against the speed of light. I guess the speed of light's what, 0.5 arguably, or 0.1. Used to be, we were clearly a factor of 1,000 bigger than the speed of light limitation. You can do the arithmetic. You have to figure out the size of the machine. But one other thing, this table is fascinating. You can learn a lot from this table. Let's look at the table a second. So here's the Intel IPSC-1 with a 286 processor and then a graphics card attached to it. So this is a GPU, the VX. And now my arithmetic time goes from 50 down to 0.33, so up by a factor of 100, so a factor of 30, I guess, 50. I can't do my math, 150, there we go. So my alpha just went up by a factor of 150. Oh, that's really bad, right, from a parallel computing standpoint. So do you take this, yes or no? Well, first of all, the guys gave it to me for free because I was friendly with them, right? And it made my code run faster. So even though from a parallel standpoint it doesn't look good, but you know, you're running faster. So the answer is you take it, right? Okay, now we jump here. This is also interesting. We jump now to the IPSC-2, which was a 386 architecture. So what happens to my latency? Let's compare the latency goes down, right? And so does alpha goes down because, the TA goes down. The latency goes down because I have a faster clock processing the MPI stack. It wasn't MPI back then, it was something else. Okay, the bandwidth doesn't, and the bandwidth improves significantly also. And then again, you get the IPSC2 VX and so on and so forth. But largely what we've seen is the non-dimensional latency has gone up a little bit and bandwidth's typically around 5 to 10. What does this 5 to 10 mean? In the time I can do 4 million operations, I can send 1 million words to another processor. Okay? And then the alpha says in the time I can do one operation, or 5,500 operations, I can send 1 word to another processor. All right? So you can see how latency is so important. I'm going to send you something, I'm waiting for a reply, I can, in the meantime, do 10,000 operations. Okay, so let's now use those values and do some analysis. So simple point Jacobi iteration, it's a good starting point just because we know what its complexity is. 14 operations per grid point. Communication, I have 6 messages to send. They are of size n over p to the 2/3, and then this is beta here. So alpha over m2 is beta. And then if we go from Jacobi, we'll look at conjugate gradients. So we have a little bit more work per processor and the same amount of communication, but plus we pick up a couple of log p terms for the binary fan in, fan out for the dot products. And then multigrid, work goes up a little bit more. And then we pick up an extra log p term due to the, more or less due to the coarse grid solve term right here. So that's the log p term that's there. Okay, and so that's full V cycle, I think, and I think that was with one smoothing step on each level. So let's ask now, how many points per processor do I need? So for Jacobi, you grind out the numbers. You equate the communication time to the arithmetic time. And you find out for blue gene or blue gene P or Q, you need about 2,000 points. So that's what we saw from our PDE, from our Navier-Stokes solver. Okay. And for conjugate gradients, as I mentioned, we have this matrix vector product and then a few extra operations with these 2 dot products. And this log p term now, with Jacobi, we had no p dependence, only n over p. Now we have a p dependence, so if p is 1,000,000, we'd need about 8,500 points per processor. If p is 1,000,000,000, we'd need 12,000 points per processor. However, on blue gene, it doesn't cost that much. There's no log p term for the dot products. Because the dot products are done not in software, which here's the log p dependency as you go from 16 processors to 500,000. Here's the same dot product cost as you go from 16 processors to 500,000 processors when it's done in hardware. All right? So what happens is we go back to our model, and we find out that we only need 1,200 points per processor. So we've gone from 12,000 points per processor to 1,200, which means the following. We are now running 10 times faster. It's not that the dot product was costing us 10% of our time. It's that it was preventing us from scaling out. Now we can scale out to 10 times as many processors, run in 1/10 the time. Same power, right? Because I have 1/10 the time, but 10 times the number of resources. Okay? But I can run 10 times faster because we've gotten rid of this bottleneck. Just to kind of hit this point home, the dot products in our Navier-Stokes code, exactly the one I showed you, the big 217 pin bundle. This is the amount of time spent, and I didn't count how many times I'm doing an all reduce, and I didn't count how many coarse grid solves I do or how many nearest neighbor exchange. I just look at the breakdown of time running on 65,000 processors of Blue Gene P. You know, the amount of time spent in the all reduce is minuscule compared to the amount of time spent in the other communication routines. So having this fast dot product actually manifests itself as quite a gain. Okay, now multigrid, it looks like we probably need about, for 1,000 processors, about 13,000 points, and for 1 billion processors, about 22,000 points. This is the complexity argument. I actually wrote code and then counted everything just to make sure my complexity argument was correct, because it's easy to make a mistake or, I don't believe I know anything until I coded it. So then I ran the code against the model, so you can see that the model, at least it looks like they're in the right ballpark. And so what is this? This is our different numbers of processors, and this is n over p. So going n over p equal 1 out to around 10,000 here. So you see the breakpoint's roughly what we predicted, right around 10,000. And well, this is the prediction, and then this is the measured values. So returning to our original question, are we doing okay? Well, we've now established some context, right? A PDE that is representative of most of the physics in our code. It's a mixture of conjugate gradients and multigrid, so we could argue with a little bit of hand waving that we should be at about 50% parallel efficiency for 2,000 processors, 2,000 points per process. And this is something that concerns me gravely since for about the last year. And you'll see why in the next slide. So the question is, what about more complex nodes? GPUs are more complex nodes. And a major concern here, which does not get a lot of airtime, is n sub a half. And there was a guy at Argonne, he's now gone, Jed Brown, but he mentioned to me n sub a half 3 years ago. He just mentioned it. I was like, yeah, okay, I could kind of see that. But it wasn't until a year ago that I realized, oh, yeah, actually, it's everything. So n sub a half, let me define n sub a half. N sub a half is the value of n, or in our case, n over p, the problem size on the node, where your node performance, it reaches half, is at half of its peak for your application. So you run a problem, a bigger and bigger problem, and you saturate at some gigaflop level or megaflop level, right? And n sub a half is the value of n where you get half that value, all right? So if you're running with an n smaller on each processor that's smaller than n sub a half, you've already hit, at this point, you're at the 50% parallel efficiency mark, right? Because you're only getting half your speed out of your processor. So that establishes a new source of granularity, a new threshold on granularity. And where it hit me was on some GPU timings we were doing on Titan. So we looked at just one GPU, no communication. Here's this blue curve. And we have to be over 100,000 points for this electromagnetics calculation on each node of Titan. And below 100,000 points, we start rolling off the asymptotic performance. So this is time. As I double the problem size, it takes twice as long, double, double, double. Conversely, as I cut by half, 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 oh, suddenly it doesn't go down by a factor of 2, right? So you can kind of eyeball that it's 100,000, and you look at the numbers, that's a pretty reasonable thing, about 125,000, which says if I have 250,000 points in my problem, I can only use 2 GPUs, not 4. Okay, that's the idea. So it's really interesting. It's just a little bit of math. the n sub a half requirements for a candidate node to yield speed up. So somebody comes to, here's your new node. It's 100 times faster than your current node. Do you take it? You work for the government, you're at an educational institute, you get it for free. So okay, I'll take it. You know, they're trying to hire your students or whatever. You know, you get it for free. Yeah, I'll take it. Oh, there's a catch. Your problem has to be 1,000 times bigger per node. Oh, okay. Well, guess what? Now you're going to be running 10 times slower, because instead of running on 1,000 processors, you can only run on one, but it is 100 times faster. Your time to solution has just gone up by a factor of 10. Okay, so that's what the math says here. Eta is the parallel efficiency, which we're going to set to a half because we're going to choose n over p to be, well, for a given problem size n, we're going to choose a number of processors to be n divided by n sub a half. So we're at the 50% parallel efficiency, all right? So the total time to solution is my intrinsic work, in other words, the number of flops per grid point, all right, divided by the speed on p processors, which is parallel efficiency times speed on one processor times p processors, okay? And eta is now a half. So here's the 2 coming out. So a half in the denominator becomes a 2. I end up with 2 times my intrinsic, which is intrinsic to the algorithm, times n sub a half times S1. So if he says, guess what, it's 100 times faster, but n sub a half has gone up by a factor of 1,000, your time to solution has gone up by a factor of 10. So this is really something we need to pay close attention to, okay? And that's why doing strong scaling studies is very important. You need to know what is the n sub a half, even on a single node. Okay, so I'll close there. You know, we're interested in getting good performance for CFD, PDEs in general, and HPC. Definitely pays to know your model and your physics, you know, if possible. I mean, RANS versus LES, factor of 10 to the 4th. It's not to be trifled with. PDEs, the choice of discretization, can yield up to an order of magnitude savings. Fast solvers, we didn't talk too much about it. I mean, you know, can get a factor of 10 to 100. In fact, for our piston case, I think we can still get another factor of 10 out of there. We're not as low as we'd like to be. Maybe a factor of 5. And then HPC, understand your single node performance over a range of n. That's important. Examine your communication costs. And all of this involves modeling and measuring. It's almost as interesting as the original physics. You can have a lot of fun doing this. So I'll stop there and take questions. Thank you.
I was just going to ask, it should be a quick one. As a grid generator, your grids are very pretty. What do you use?
That was done by a postdoc at ETH Zurich using Qubit.
Qubit.
Yeah. Yeah. And
the other ones were very pretty. I mean, all of them I saw seemed very nice.
Right, yeah. Yeah. That one was with Qubit. I mean, this one right here in particular was done with Qubit. Some people are using TrueGrid, and some of them are using some kind of homegrown software. Yeah. I don't know about the airfoil one. I'm not sure what they used for that one. But, yeah.
Several groups now, when they do, for example, discontinuous Galerkin approaches, they choose one volume per rank already.
Right.
So do you have any idea of how to break a strong scaling barrier on this? So this means I can only go to a number of processes which maps my number of elements.
Right, so what order are they running, do you know?
15th probably.
Well, so they could go to 8th order, and then they would have, you know, 8, and then they'd have a factor of 8. I mean, that limit would go away.
Yeah, but would this actually give us a benefit?
Okay, so
down with order, you also choosing the work.
Right. So, yeah. So that's it's a common question for us. Just take the 1D for example. You know, two elements of polynomial 8 each are one of polynomial order 16, and the cost function is kind of complicated, especially in 3D. One of the issues when you go to n equals 16 for an explicit time stepper is the time step size goes like 1 over n squared. Okay, but the accuracy, there's a significant accuracy gain. Like I say, most of our users fit in kind of the 8 to 12 is a very common one. But if you really wanted to scale, you know, and this assumes that you have some liquidity in your mesh also, right? Because you know, you could go to polynomial degree 10 and have a different mesh. So you have some flexibility there. Because you can't do the following. What you can't do is say, well, polynomial 8 with 2 elements is less accurate than polynomial degree 16. I mean, that may be a true statement, but maybe polynomial 8 with 2.4 elements, you know, there's some trade-off there. But 15 sounds pretty high. If you were sitting at 8 or 6, I'd say, yeah, you can't really shave it down too much.